Pradip. So we get started with the first talk from Pradip Dey. He will present some results that he obtained when he was a PhD student and a postdoc in Freie Universität Berlin. And now he's working in Tel Aviv University in the group of Ronnie Sachi-Fainaro. So Pradip, the screen is yours now.
Okay, so you can see everything, no? Okay.
Yes,
good.
We can.
Oh yeah, thank you, Marcelo, for the kind introduction and also for organizing such a nice symposium. Hopefully, we'll learn something new. And so today, as Marcelo mentioned, I will mainly briefly talk about the work I did in the group of Professor Rainer Haag in Freie Universität Berlin, and it kind of deals with a little bit what is happening nowadays now. So if you see that how viruses interact with the cells and go inside, there is a key parameter which controls all these informations, like there are heparan sulfates present on the cellular surface which interact with the only in this case I am discussing with the herpes viruses, which interact at first electrostatically and then bind together, and then it helps further endocytosis. So but there are very few antivirals are available, but which they are mainly targeting they are using small molecules, as well as they are using some proteins which can generate immune response or the oligonucleotides, but they are mainly working on mainly intracellular. So there is nothing which can work on extracellular basis or kind of inhibit these processes. So if you want to learn multivalency, then you can see that if you consider that how pathogen goes inside the cells, they use kind of a multivalent interaction present on the cellular surface as well as in the viral capsid, and this is how they internalize it. Now if you use this kind of a small molecule based some kind of inhibitor, then you need much more to inhibit this process, whereas if and these bindings are kind of reversible, so it's not so easy that you can inhibit such processes. Whereas if you have such a multivalent architectures in a polymeric scaffold or some nano platform, then this process is more feasible, because if one interaction goes away, then also there is steric shielding effects which can inhibit this uptake of this foreign particles. So based on that, in our group have developed some kind of inhibitors which on TRGO base, so where they functionalized with polyglycerol at first, and then they do sulfation to have the negatively charged surface, and which kind of mimic the heparan sulfate proteoglycans present on the cellular surface. And with this kind of TRGO surfaces, they could show that they can interact with the orthopox virus or HSV1, and they find out that the size around 300 nanometer was most perfect. And in the meantime, so we came up with the idea to understand what is the effect of flexibility towards this inhibition of these herpes viruses. So so for that purpose, we came up to find out a suitable balance, that we prepare two different kind of nanogels. One is consisting of the rigid one, which will mainly consist of the cross-linking by the hyperbench polymers, and we thought to cross-link with some linear polyglycerol, and which could act as a flexible one. And we wanted to understand how this kind of flexibility or deformability of these nanoparticles influence this inhibition. So during this time period also there is a paper came out, it's in Nature Materials. So what they discuss is that if you have a small linker, so what they did, they functionalized a 2 to 3 nanometer size gold nanoparticles with some sulfonated molecules, and similarly they only changed the spacer length. And what they found out, that if you have a flexible spacer, then it leads to kind of a irreversible binding with the viruses, whereas if you have a small or rigid linker, that it could kind of this complex is not that stable, so it can infect. So based on that, so this kind of strengthened our strategy, and what we did, we used the nanoprecipitation technique to prepare such nanogels. So here I used dendritic polyglycerol sulfate containing few azide groups, and we cross-link we functionalize some cyclooctanes with dendritic polyglycerol, and we thought this will form the rigid nanoparticle, whereas if we mix this instead of using this hyperbond polymer, we use this linear polyglycerol with some cyclooctanes, and if we cross-link them, that will form some flexible particles. So this principle is very simple. So what we do, we mix this polymers in water, and then we in a dilute condition, and then we precipitate it out in a non-solvent. In this case, it was acetone. And here this acetone and water is miscible, so what it does, it upregulates the concentration inside these tiny droplets, and which initiates the cross-linking due to rapid increase in the concentration. And after certain time, this cross-linking will so it stabilizes the particles, and then if we transfer them into water, so we can get such a nice nanoparticles, and then we can do dialysis to remove the rest of the solvent. And this afterwards we did kind of a we characterize them by dynamic light scattering as well as an NTA. So what we find out that this we prepare three different nanoparticles, one with rigid nanogel, one with flexible, and the other one is control nanogel, which was devoid of these sulfate groups, which was consisting of only hydroxy groups. And we characterized that how much sulfur is present. From there we could calculate how much DPGS was present inside this nanoparticle, and we also could show that these particles has kind of a negatively charged. And then we also tried to see how they are looks like by AFM, but in that case we used a positively charged surface. So this was this mica wire polylysine coated. So then we tried to adhere such nanogels, and what we find out that based on their flexibility, they had more width compared to their height, and this could be reflected from here, that if we plot their height and width, what we see that for these flexible particles, the width was like 6.2 times higher than their height, as well as for the rigid ones, this was only 2.6 times. And which somehow kind of gives some evidences that due to this kind of multivalent interaction, they are kind of flattening on the surfaces compared to their rigid particles. Similarly, we did also some Q&M, like we did deformation study. So what we could extract from there, that these flexible nanoparticles could be deformed to the 62% of their original height compared to rigid particles, which are around 10%. So then we collaborated with a group in FU Berlin, the virologists. What they do, like they first tested the biocompatibility of these nanoparticles, and what we find out, these nanogels are kind of is good, and but their cell viability was very nice. And then we did infection assay. So this infection assay was done in two different sides. One is the post-infection, and another one is the pre-infection. So pre-infection means at first we mix these nanoparticles with the viruses, and then we introduce into the cells. What we find out that really our assumption was correct, that flexible particles had EC50 value around 90 microgram per ml, whereas the EC50 for this rigid one is around 165 microgram per ml. And then we also tested in a post-infection model, though it was not so successful. What we find out, like post-infection means if we infect the cells and then we introduce the particles afterwards, and what we find out that all the nanoparticles were not that much active in that model. Then the reviewer asked us that, okay, you saw something, but still we don't have the affinity. That how can you compare these flexible and rigid particles? They thought that the interaction could be more strong for the flexible ones, but that's why we thought to check it with a positively charged nanoparticle. So what we did, we used some positively charged nanogels, which are at first coated on a gold surface, and it is this SPR sensogram. And at this time point, now if we flow these rigid nanogels, you see there is an increase, and these delta R values are noted in the table. So what we can see that to cover the surface for this rigid nanogels is very much material to cover it, whereas for the flexible ones, the thickness was not that much because all the delta RU connects to the thickness of this film, whereas these control nanogels are not binding that much. Then after saturation, if you wash them, what you can see that this interaction was that much strong that they were loosening up. You see the similar behavior with the rigid nanogels, but for the flexibles one, so there was no dissociation. So which kind of passively tells us the story that what we saw in the AFM as well, that these flexible nanoparticles, you need much less number of molecules to kind of passivate the surface. So based on that, we calculate the contact area considering this simple virus has some kind of a diameter of 200 nanometer. Now if we calculate the surface area, it is around this. And now if we consider the width of this particle, and from there if we calculate the contact area, and what we find out that you need at least 5 to 6 nanogels to cover the whole surface or whole particle, whereas only 3 particle is enough to do so. Based on that, so we summarize the talk in a way where we could show that these particles have, so what we show that these nanogels kind of acts as a broad inhibitor for this kind of viruses, and as well as the sulfated particle could show that inhibition, whereas by tuning the flexibility we could show that we could kind of stoichiometrically balance this kind of infection. And I did not discuss about that what is the fate afterwards after this interaction, and what we see that these nanoparticles, when they complex with these viruses, they does not go into the cell, whereas if you don't add the nanogels, they are going to the cells. That's all from my side, and thank you for listening.
Thank you, Pradip. Thank you for the very nice talk. We have already a question in the chat. So from Oliver, I guess it's from Oliver Etzel. He has a very interesting talk. My question to Pradip is how he will translate those gels into an applicable formulation, for example, against a virus replicating in the mucus of your throat.
So I only think of could be useful for lungs, but I am not so sure how can you put it in the throat. For the lungs, I could think of something.
Okay, and how will you formulate? Like, how will you apply?
Like a spray, like a spray.
Okay, okay, very good. So do we have another question? We have time for one more question. Somebody wants to raise their hand? Okay, I have a question there. You have some results that you didn't present about post-infection and pre-infection. You didn't mention the pre-infection part. What is this? Is sort of
sorry, I couldn't hear. What was?
So here, what is the meaning of pre-infection? What is the study you do? This is a sort of like a sort of not a vaccination, but somehow to prevent the infection of the virus in a person?
Yes, yes. So pre-infection means you at first inject, like you mix your nanoparticle with the viruses.
Okay.
Okay. And then you introduce the cells. So there we see that it is acting very well. Like it can be used as a prophylactic. But on the other hand, if you have a infection already, let's say if you infect the cells already, after 1 hour, you incorporate the nanoparticles, the results are not so good because this is not working that well intracellularly.
Okay, okay, perfect. Thank you, Pradip. Thank you from everybody, I think. Thank you.